So let's try to do this. You really have to do me a favor and go through the technical material, otherwise there is no way that we can do this seriously within the time frame that we have available. So make an effort, please, to read the thing. So briefly, what is it you're going to find? You're going to find that the question you're going to ask is, what does the dynamical system, because it's the dynamical system we're studying, right? Does an initial condition somewhere here at x0. We know it has to start from one point on this line. Those are feasible. But it's a funny mechanism. If you think of the economics behind it, the economics actually is meaningful because I'm sitting at x0 and I'm thinking, which x1 should I pick? Because I pick x1. I don't pick x2 in the first. But whatever I get from x1 depends on what they pick from x2. Because that determines how much I consume. Right? If I pick x1, I know the marginal productivity of x1. F prime x1, right? It's in the payoff. But I don't know the price at which I value it, because if they decide to invest very little, so x2 is small, then there's a lot of consumption. It's not worth a lot. And if instead x2 is also very big, then there's little consumption. Then the extra consumption is worth a lot. So my valuation of x1, my choice, I'm the guy sitting in the first period, depends on other people's choice. So there's a way of thinking of the infinite horizon model as actually a sequence of traders. I don't want to go difficult. Or a sequence of individuals that try to make forecasts about other people's choices. It becomes much more complicated, obviously, but it opens up. And those people sitting next period, or will come next period, will also to make choices, thinking, what will the other people choose? And so on. It's a chain looking at infinity, which is typical of economic environment, where there are markets where people have to invest today by betting on expectations about what people will invest tomorrow, and future prices. Right? So you can get the old theory of temporary equilibria a la Hicks, Grammont, and company out of this. Obviously, we studied the super simple thing, which is, let's pretend people can, exactly forecast. But again, don't ever fall in the nonsense, bullshitted argument. We don't believe that people can forecast forever. We're perfectly aware how complicated it is. Point is that it's so complicated that we better start studying and understand at least the basic, super elementary thing to have a reference point, and then from there it says, well, the people may screw up. They may get over optimistic, then my path goes that way. Then they get, right? So nobody's that dumb to think that you're sitting there in 1700 and you forecast, Tesla investment 300 years later. It's not the way it works, okay? So that's one way of thinking at it. It's this sequence in which what's good was not good. So where I start here, it depends on where it goes. So the asymptotic behavior is crucial. And I do know from Mangasarian theorem there are all those infinite paths. Because from any point here, any point you pick, once you put it in the dynamical system I wrote before, that system now is fine. It's going to be running and it's going to determine a sequence, a whole trajectory going to infinity. So given any choice on that vertical line, there will be a path that will satisfy the Euler equation. An infinite number of them. And I know from Mangasarian that only one of them is optimal. All the others are suboptimal. For whatever reason, they don't solve the problem. Okay? So the mathematical task became, well, which one is the good one? Funny thing, there are many ways of approaching it, and dynamic programming, as we'll do in a second, is in my opinion by far the most efficient, and also I think mathematically simpler to understand. But to put things in perspective, and also because it's relevant for von Neumann, the saddle point theorem and so on, and to understand some of the things you're reading about growth theory, at the beginning people didn't go that way, people went another way. They said, okay, it's a dynamical system, it's complicated, but let me see what happens around the steady state. I do know that the steady state is optimal, you see? Why? Because if you start from the steady state, it's optimal to stay at the steady state. It satisfies the Euler equation, and obviously it satisfies the traversal condition. Right? So from this initial condition, x star, so when x0 is equal to x star, for sure this is optimal. Right? You understand? Well, let me see what happens around. Around, what is it people do? They linearize. So you take that Euler equation and you linearize. A bunch of theory, you gotta go read it. You know, it's algebra, it's good algebra, it takes a little bit to get, you just linearize. It's a 2x2 dynamical system. You take first derivative, you compute the, what is that called? The Hessian, I think, no? Is that called the Hessian? I forgot. Anyhow, the matrix of derivatives with respect to each one of the variables. You evaluate those derivatives at the steady state. You compute the eigenvalues, right? And that tells you, using the elementary theory of dynamical system, what's the local behavior around here. Because to each eigenvalue you associate an eigenvector, which defines locally, in a small neighbor of that, a direction in that space. Well, what it turns out that this steady state is a saddle point. That is, the two eigenvalues are one larger than one and one smaller than one. Actually, the theorem in general, which is a variation of the theorem on Hamiltonian from classical mechanics, says that there are for sure, if the system, this can be replicated in dimension n, right? I forgot now what the original theorem. I think there's a theorem of Poincaré that started out the game, and then these are called perturbed Hamiltonian because of the discounting, and Hamiltonian does not have the discounting. I think that what you prove is that in fact, in an n-dimensional system, which so the dimension is 2n, there are 2n roots, n of them are certainly larger than 1. And the other n will depend. Okay? In fact, part of my initial research when I was young was trying to figure out what happens to the other n and show that sometimes some of the other n may all be unstable, and nevertheless the thing can be handled. Okay? But there are cases, we know of cases, I mean, I produced some of the examples with the master, Montrucchio, in which that steady state is completely unstable. So all roots are larger than 1, and nevertheless the system is stable. But that's complicated stuff. If you want to study it, you study it later. Now, okay? So simple case, just as usual. I teach you the simple case and say whatever is true for the simple case is not true in general. Okay? So this in particular is not true in general. But for the simple case, it's a beautiful theorem. The two roots split. One is larger than one is smaller than one. Hence, in the simple case, this is a saddle point. Saddle point has a stable manifold, locally, and an unstable manifold. What it means is that points starting on the unstable manifold move away, tend to go away. Points instead starting on the stable manifold, let's do it in blue, come back in. Right? Because along the trajectory here, if you are on the stable manifold, the eigenvalue driving you is the one less than 1, so values are contracted. Deviation from the steady state gets reduced. Right? So this point is attractive along this trajectory. And it's not. So remember the point here going and come back, right? For dimension, right? Alright. Now the story is long. For the simple case, Cass in the continuous time, Koopmans in discrete time, proved that this is true globally. That is, that these manifolds, in particular the stable one, extends globally for all initial conditions. And so it's very simple. When you get an initial condition, you look where it crosses the stable manifold, and that's x1. And from then on, you're done. So if you start below the steady state, you go up progressively toward. If you start above, you go down progressively toward steady state. That's the theorem. It's in Cass for the continuous time, in Chiali and Koopmans for the discrete time, the one you have here. They're not proved with exactly these techniques. They're a bit, the first time people don't see things so clearly. That's why it's difficult. They find a way of proving it. I think Cass' proof for continuous time is very beautiful. Koopmans as well, right? Anyhow, there's an interesting anecdote. Apparently, you understand, Hirofumi Uzawa was David Cass' advisor at Stanford. And Hirofumi Uzawa and Chiali and Koopmans always had some kind of personal competition, and probably they didn't like each other. Having known well Uzawa and met Koopmans only once, I can see why. Uzawa anyway, I can see the reason their personality would not match. And they were in eternal competition at the time, because they were the two brilliant people doing, how can I say, the simple growth theory at the time, but one fashion because it was aggregate. There were people doing complicated things like Mackenzie and Radner and improving, but that was a bit of a mathematical economics out their group. The Uzawa-Koopman stuff was more accessible. Anyhow, they were in competition. At the time, obviously there was no internet, nothing. People would ship papers, typed paper from one another by mail. And so Koopmans, all happy, sent to Uzawa his paper proving this for the discrete time model. And right at that period, Cass, David, was younger, had just finished proving his version for the continuous time model. That, frankly, in my opinion, is a bit better than Koopman. It's more elegant, more complete. And so Uzawa, at this moment, all alone, he decides to humiliate the other guy. So he sends back a letter saying, "Thank you, Chiali, this is very kind of yours, beautiful results. I'm enclosing a paper that a student of mine has just completed. And as you see, he can prove blah, blah, blah." So I said, "But it's a nice result, but on the other hand, isn't it obvious?" So I decided he has to write a little bit more before getting a thesis for it. This was completely out of the blue. It was not planned. David was supposed to go to the market. He was told by Uzawa, says, well, they loved each other actually. I met Uzawa through Cass, who was a very good friend until he died. And so that was, you gotta stay open. You cannot go to the market, this you gotta write more. And obviously the thing was, Cass being the most brilliant in the group of Uzawa student at Stanford, what was true for Cass had to be true for everybody else. But the first person that told me the story was Carl Schell. They said, therefore, I had to postpone to the market because David was staying on. Then I asked if David was true. He says, yeah, something like that was true. He pushed us farther because he didn't want to give Koopman satisfaction. So, that's competition. It's interesting. You don't have to take it too bad. Anyhow, so this is the stuff these guys proved. Then the thing went on. This is in the middle 60s. It took until the middle 70s, so it took about 12 years of research on the thing by pretty good people to show that this, under much more restricted conditions than those I just gave you, is true for the general model when there is enough discounting. And that's actually Jose Shakeman neighborhood theorem in his thesis with Lionel, and then Brock and Shakeman, and then Lionel himself and a bunch of other. But that's, you have it that's technical stuff. So now we know that something like this is true under strong conditions for the general growth mode. That we can go to the balanced growth or the steady state if you like. Okay? But it's not true in general at all, and all kind of complicated behavior cycle, chaotic behavior can arise. Okay? That's also complicated stuff we will not discuss. Now, one thing I want you to teach you though, which is to see why in the one sector model this is always true, and why it's special, and see the economic meaning of it, because I think you'll learn something about economics in that. And to do that, we have to use dynamic programming. Okay? But then, so I assume you know what a value function is. And if you don't, you will study it. Alright? So this problem can be written in a dynamic programming formulation that allows it to become recursive by defining the value function of an initial stock to be the solution to this, okay? And then showing that the value function, just basically you compute the total value of the optimal program, that's a number, right? That number will depend on how much stock you have, because that's the only thing, right? Well, you repeat that exercise, whatever initial condition, you get a function. That's the value function. Well, that value function satisfies a particular set of restrictions that turn out to be very elegant. It's called the Bellman Equation. Richard Bellman figured it out first. He managed to use a theorem, a fixed point theorem by, what was the name of the guy, the German guy, Banach, right, for complete metric spaces, blah, blah, blah. You go, if you don't understand, we'll go through that, but, point is that the value function for a generic initial condition X satisfies this. Right? For all periods and for all pair Y in gamma of X, where gamma is that feasible set I defined before. So it is anything between 0 and f of x. Okay? So for every x, there is a set of feasible values I can pick, and that's it. And x is a state between 0 and x upper bar. Okay? So that's a very simple formulation in the dynamic programming world. Alright? Value function is concave, continuous, and in fact increasing in the stock. More capital I have, more happy I become if I do things right. Okay? Notice the same function. Okay? So what was the observation? The observation to make things simple was first made in this proof by two friends. I think it's D. Deckert and Kazuo Nishimura have it in some paper in the early 80s or late 70s in JET. Don't worry about it. I mean, the paper is actually about something else, but they had this beautiful idea. They said, look at this. He says, this, if you think of it, this is the problem you solve every period to figure out the optimal sequence, right? So you start at x0, and that gives you x1. Then with x1, you find x2, x3, right? And so on. All right? And this is a function in dynamic programming. That's the big advantage. It's a function of, that's why in dynamic programming, once you prove the existence of the value function and compute it, you don't have to go crazy with the transversality condition, all that stuff. You just start with the function, it's called the policy function, that maps today's stock into tomorrow's optimal stock. And you just iterate this recursively, because the problem is time invariant. The only thing changing is the state, right? That's the beauty of it, okay? So their observation was, look at that, that's a sequence. And so basically what this thing gives me is this, xt plus 1 optimal equal tau of xt optimal, okay? If I want to study the dynamics of that sequence, all I have to figure out is, something about this function. In particular, this is a function from an interval on the real line into the same interval on the real line, and the function is continuous. If I show, and I know it has a fixed point, in fact I can actually show it as an interior fixed point, right? In other words, if I go back and I draw a square, right, I know that that function from xt into xt plus 1 for sure crosses the 45-degree line at x star, right? And nowhere else. Everywhere else it's either above or below. All right, here is what I want to show. I want to show, and remember that it's bounded, right? There is x bar, there is the maximum amount. Right? Here's what I want to show. I want to show that that function is monotone increasing. Right? That is, it always goes up. I want to show it's monotone increasing. If I show it's monotone increasing and it maps the interval into itself, then I'm done, because, think a moment, it has to be like that. In particular, it cannot be like that, right? Because it would be forced to have another fixed point at xx, and it doesn't, right? See the argument? Geometrically simple, no? So all you have to do is to show that it's monotonic increasing. And how do I show it's monotonic increasing? Well, I take two initial conditions, two x's, call it x1 and x2. I solve that, and I show that if x1, well, say x2 is larger than x1, then the optimal y2 is larger than the optimal y1. Okay? You understand? So, function is like that. It's a square segment mapping into itself. For sure it has a fixed point. For sure it's interior. For sure it's continuous. Therefore, it has to be like this if it is monotone, because if it were not like that, notice that if it is like this, that point is stable, right? That's the point. Under iteration of the mapping, you converge to the point. If it were otherwise, say like this, it would have to have another fixed point here. And well, and another one